This video will cover Chapter 3 of the OCR A Chemistry Specification, Amount of Substances. So in this video, we will be covering all of these specification points down to the right hand side of the screen, and the pages can be found here on Kaburu. In this chapter, there are a lot of definitions. The first one being the definition of 1 mole. Now, a mole is the amount of substance that contains 6.022 times 10 to the power of 23 particles, which is the Avogadro's constant. I'm sure you know this from GCSE already, and it comes up a lot in A-level as well. Now, moles are not the same as molecules. Hydrogen as H and H2 are not the same. They are both 1 mole because in front there is 1. However, hydrogen is 1 mole of the hydrogen atom, whereas H2 is 1 mole of the hydrogen molecule. Moles is dependent on the big number at the front. It is not dependent on the little number. Therefore, although these two are different in terms of one being an atom and one being a molecule, they are both still 1 mole of hydrogen in a sense. Another definition that you need to know is the definition of molar mass. Now, molar mass is the mass per mole of a substance. So the mass per mole of a substance. Per means that we can give it the units grams moles to the -1, because this just means grams per mole. Therefore, using these units, we can deduce that there is a very key equation that links mass, moles, and the molar mass of a compound. This equation is right here. Moles is equal to mass over molar mass, or mass is equal to moles times molar mass, or molar mass is equal to mass over moles. Now, I'm sure you've come across this triangle before, but if you haven't, this triangle allows us to remember all 3 of these forms of the same equation, but just in one triangle. If you have moles and you don't have mass and you have molar mass, then you can cover up mass and see that it's moles times molar mass. Now, there are two more definitions, that you must know for this chapter. Molecular formulae. This is the number of atoms in each element in a molecule. Empirical formula is the simplest whole number ratio of elements in a compound. Now, this can be fairly confusing. However, I believe this explanation does explain it fairly simply. For instance, let's say we have a compound like C3H8, or as a better example, C4H8, Now, this C4H8 is the molecular formula. The reason why this is the molecular formula is because this is purely just the number of atoms or elements in that compound, right? So there's 4 carbons, 4 hydrogens. No more, no less, because that is simply what that compound is. It's got 4 carbons and 4 hydrogens. However, we can see that 4 and 8 are both divisible by 4. So the simplest ratio would be CH2. Reason being, because they're both common multiples of 4. Now, this extends to something like C6H12. They're both multiples of 6, so it's CH2, right? Something else such as C3H12 as well. That would be CH4. So it's simply just the lowest whole number ratio of elements in a compound compared to the number of elements in that compound as it is. Now, for this chapter, you need to be able to calculate the empirical and molecular formula with information that's given to you in an exam. An example is shown here. In an experiment, 1.203 grams of calcium combines with 2.13 grams of chlorine to form a compound. We're given the molar masses, and we're told to calculate the empirical formula. Now, this is a very, very common question that you'll see in an exam, and we'll run through how to answer it here in steps. Step 1 is you use your mole triangle to see what is missing. So we'll write out the mole triangle. Moles, mass, molar mass. Now, looking through the question again, I can instantly spot, okay, there, I've got mass. So I've got mass, I'll take that off. And I don't have moles, but I do have molar masses. So I've got molar masses as well. So now, I know, I've identified that moles are missing. Next step is to calculate the missing component for both compounds. Right, now reading the question again, we know that in an experiment 1.23 grams of calcium combines with 2.13 grams of chlorine. So the two elements that we need to be able to calculate the moles for is calcium and chlorine. So first we'll do calcium. Well, from the triangle we can see that moles is just equal to mass over molar mass. So for calcium I'll just do 1.203, which is what we were given, divided by the molar mass of calcium, which we were given in the question, 40.1, or is given in our periodic table. And we can just plug that into the calculator and we get divided by 40.1, something like 0.03. Now for chlorine, we'll just do the exact same. We were given 2.13 grams, divide that by the molar mass of chlorine, which is 35.5. And that gives us 2.13 divided by 35.5, 0.06. Now, of course, these don't make any sense. So to get the empirical formula, what we have to do is divide both of these numbers by the smallest mole. So the smallest number out of the two. The smallest number is, of course, 0.03. So we do 0.03 for calcium over 0.03, which gives us 1. And then for chlorine, we'll do 0.06 divided by 0.03, which gives us 2. So the answer is we have 1 calcium, 2 chlorines, CaCO2. The empirical formula. Remember, empirical formula is the smallest whole number ratio, which was given by these examples here. This is what we've calculated. The numbers here, that 1 in 2, that 1 in 2, that 1 in 4. Now, you can also, of course, be told to calculate the molecular formula. Now, if you are told to calculate the molecular formula, there's a very specific additional piece of information in the question that is always given to you. And that is here at the end. The relative molecular mass of the compound equals 180. We'll come to why that's important, but just know that that is very specific for a molecular mass question. So, a molecular formula, sorry. So, the question is, chemical analysis of a compound gave the percentage composition by mass of a compound as carbon being 40%, hydrogen being 6.62, and oxygen being 54.33%. We have the molar masses, and this is, we're not told because I forgot to write it, but this is the molecular formula question. Calculate what the molecular formula is. Oh, right here, calculate the molecular formula. Right, so, step 1, to calculate the molecular formula, sorry, let me just drop this down here, is to do these steps 1 to 3 above the exact same. Now, this is a percentage composition for a question. So what we have to do is we have to take these percentages as masses, right? So if we're doing that, then pretend these percentages are masses, then we know that we've got masses for each element here. We've got the molar masses. So if I'm writing out this triangle, moles, mass, molar mass. Okay, well, I've got the mass as percentages, right? So just a quick briefing as to why we are allowed to use these percentages as masses is because we know that these are all the elements. Adding up these percentages gives us 100%. Therefore, ratio-wise, I know that 40% of carbon is the same as 40 grams of carbon if my total mass is 100. That's why we are allowed to use percentage composition as our mass. So we have our masses, we have our molar masses of each element, so now we just need to calculate moles. So then I'll split it up as carbon, hydrogen, and oxygen. Moles is equal to mass over molar mass. That means that is for carbon, 40 divided by 12. For hydrogen, moles is equal to mass over molar mass, which is 6.67 divided by 1. For oxygen, moles is equal to mass over molar mass, which is 54.33 divided by 16. Equals. So 40 divided by 12, 3.3, 6.67, 6.67, 54.33 divided by 16 is equal to 3.4. Now, the smallest out of all of these is carbon, so therefore we can just divide this by 3.3. This will give us 1 carbon, this will give us roughly 2, this will give us roughly 1. Now, the reason why we're allowed to take these as 2 and 1 is because the difference is so small in terms of decimal points that it makes no difference. For whatever reason, if this number is 2.5 or 2.45 or something in the middle like that, then we have to times all 3 by 2 because then that will give us 5, and that is the whole number. It is a whole number that we're after. However, for this example, because it is roughly 2, we are allowed to use it as 2. Same goes for the 1 for oxygen. So that means the empirical formula comes together as CH2O. So what do we do now? Now, we multiply to get 180 as the molecular mass. What does this mean? Well, this means this answer that we got, CH2O, as the empirical formula, if we add up all the molar masses, we get 12 plus 2, because there's 2 hydrogens, plus 16, we get 18, 20, 30. We get 30. But the total molar mass that we're after is 180. Therefore, we have to do 180 divided by 30, which gives us 180 divided by 30, 60. Sorry, 6. That was a mess up on my part. So this means that to get from 30 to 180, we multiply by 6. That also means that we multiply all of these small numbers here by 6, which means in the end, our compound is 6H12O6, and that is the answer. In 4 simple steps, you can get the answers. Now, these steps are universal. They'll work for every single question of this sort. Of course, maybe there is that small nitpicky difference here with the 0.5, but you just have to multiply out to get a whole number ratio. Hydrated salts. For hydrated salts, there's only one real definition that you must be aware of, and that's the one up here, water of crystallization. This is water that is part of a crystalline structure. Now on the left, you can see a compound that is hydrated. Hydrated means that there is water of crystallization within that compound, and this can be seen by this dot right here. This dot shows that there are 5 water molecules associated with the whole compound. Now, on the right hand side, you can see the anhydrous form of that compound. The anhydrous form shows that the 5 water molecules are no longer a part of this compound's crystalline structure. Now, the questions for hydrated salts are usually, what is the molecular formula of so-and-so molecule, or what is the value of X, where X is this big number. Now, a question can be seen here, and we shall do it together. So, tackling a question like this. Number 1 is you must calculate the molecular formula, or the formula mass. If you cannot calculate the formula mass, it will be given to you. And you can see that the formula mass is given to us. So we know that the formula mass in total equals 172. Now, formula mass is just the total molecular mass of that whole compound, meaning all of the molecules within that compound are accounted for to get that mass. Therefore, what we can do is work backwards. We can figure out the formula mass for this compound, and then the formula mass of water, subtract it from this, and then divide. And we'll do that right now. So, we know calcium oxide is present. This has a formula mass of roughly 40. We know sulfur is present. This has a formula mass of 32. Oxygen has a formula mass of 16. And we know there are 4 molecules of oxygen, so we have to multiply that by 4, which gives us 64. Then we have hydrogen, which is 1, multiply that by 2 because there are 2 hydrogen molecules, gives us 2, and then another oxygen, which is 16. So then we get the total formula mass that we can calculate through the question. Total formula. That's going to equal 40 plus 32 plus 64 plus 2 plus 16. 154. So then we do 172 minus 154 to get 18. Now, what we need to divide by is the total formula mass for H2O. The reason why we do this is because we know that X, whatever X is multiplying the formula mass of H2O. Therefore, expressing this mathematically would be X brackets Y is equal to Z. To get the value of X, we must divide both sides by Y. So X would equal Z over Y. And in this case, Z would be the leftover from our subtraction, and then Y would be the formula mass for water. Therefore, expressing this mathematically would be 18, because 16 from oxygen plus the 2 from hydrogen H2, X is equal to 18. Therefore, we can divide both sides by 18 to get X is equal to 1. So in this question, the answer is X is equal to 1. So just putting these in terms of steps, it would look like this. Step 1 is identify the total molar mass, total formula mass, which was given to us in that question. Step 2 is calculate the formula mass from the compound that we were given, which would be the formula mass with the X taken out. Step 3 would be subtract the total molecular mass, the total formula mass that was given to us in the question, from the calculated total formula mass, which we worked out. And then step 4 would be to divide by 18. You can just remember it as dividing by 18 because these questions are always water of crystallization questions, and water is always going to have a formula mass of 18. Right, now when a hydrated salt loses its water and becomes anhydrous, we have to assume 2 things occur. Number 1, that all of the water has been evaporated. And number 2, that no further composition has occurred. Now the reason being is because we have to assume that the weight that we got after is purely only because the water of crystallization has been evaporated away, not because we lost any of the actual crystalline structure or because some water was still left in. Now, moles is equal to mass over molar mass is good to use for solids, but what about liquids or gases? We use different equations for each of these states. For liquids, we use moles is equal to concentration times volume, where the concentration is measured in moles per decimeter cubed and the volume is in decimeters cubed. Now, this is an important conversion to remember. 1 decimeter cubed is equal to 1,000 centimeters cubed, which is equal to 1,000 milliliters, which is equal to 1,000 liters, which is equal to 1 liter. Now, this is an important conversion to remember. 1 decimeter cubed is equal to 1,000 centimeters cubed, which is equal to 1,000 mils, which is equal to 1 liter. Now, concentration is defined as the amount of solute in moles dissolved in each 1 decimeter cubed of solution. Now, that is an important equation. However, that does not come up as much in exams as the next 2. Standard solution. This is a solution of known concentration, and volume. And that is it. That is all you need to write down in an exam. That's how the definition comes up in the mark schemes, and that's completely fine. Now, the reason why standard solution is important in experiments is because it allows us to do these C1, V1 is equal to C2, V2 calculations. Now, this comes up later on with titration, so we won't go over it now. Now, for gases, a gas is also different. For a gas, we need the molar gas volume. This is the volume per mole of gas molecules at a stated temperature and pressure. Therefore, with this definition, we can conclude that the volume of a gas in a specific area is only affected by the temperature and the pressure. Nothing else will affect the volume of a gas. Now, as you can tell from this definition, that the temperature and pressure when doing calculations for gases really does matter. It will change how the equation will go. But at room temperature and pressure, there is always one equation that we need to know. And that equation we will come to later on. But we need to know specific conditions at room temperature and pressure. So the temperature at room temperature, also known as RTP, is 20 degrees Celsius. The atmospheric pressure is 1 atm or 101 kilopascals. Either one will get you the mark. And you also need to know that there's 24 decimeters cubed of volume of 1 mole of gas. This means that 1 mole of any gas at room temperature and pressure takes up 24 decimeters cubed of volume. Therefore, under all of these conditions, and no less, no more, this equation is true. That moles is equal to volume over 24. Or it can be expressed as this triangle. Hence, collating all of these pieces of information together, for a solid, we use the equation moles is equal to mass over molar mass. For a liquid, we use the equation moles is equal to concentration times by volume. And for a gas, we use the equation moles is equal to volume over 24 at room temperature and pressure. Well, we spoke about what the equation would be like under ideal room temperature and pressure conditions, but what if it was not room temperature and pressure conditions? Well, if there aren't room temperature and pressure conditions, then we use this. PV is equal to nRT. Now, this is known as the ideal gas equation. Labeling this equation, we get pressure in pascals, we get volume in meters cubed, we get moles as mole. Now we get R, which is always the exact same, 8.31 joules per mole per Kelvin. Then we get temperature in Kelvin, and that's all you really need to know. For conversions, it is very important to know all of these because these are the very normal ones that come up in the exam. Even with the ideal gas equation, there are some assumptions that must be made. Number one being that random motion of particles occurs. This means that if you have a box full of air particles inside, no two gas molecules will be moving in the same direction at the same time. They will always be moving in random directions. Number two, that elastic collisions occur. All this really means is that when two gas particles collide, they lose no energy. Number three, negligible size of gas particles. That's fairly self-explanatory. And number four, there are no intermolecular forces between gas particles. This means that as two gas particles pass by each other, they won't slow down due to any intermolecular forces. Now, to round off the content for this chapter, we just have to quickly go through percentage yield and atom economy. Now, percentage yield has one definition that you must know, and so does atom economy. For percentage yield, we have the theoretical yield. This means that there's an assumption that 100% of the products are desirable. Now, the percentage yield is trying to understand what percentage of a reaction gives you the wanted product. For instance, for something such as photosynthesis to occur, what photosynthesis requires is oxygen, and it produces carbon dioxide as a byproduct. If carbon dioxide was not produced and purely just energy was produced during photosynthesis for the plant, then that will have a 100% percentage yield. Now, you also need to know why this is not possible. And this is not possible for three main reasons. Now, these are the three main reasons as to why a 100% percentage yield is impossible. You only need to say one. One is 1 mark in the exam. And now we must go through the percentage yield, which states actual yield over the theoretical yield times by 100. And now for atom economy, you must know the definition that atom economy is the measure of how well atoms have been utilized in a reaction. You must know that high atom economies mean that the reactions A, produce large amounts of the desired product, and B, make reactions sustainable. Hence, better use of natural resources. The equation for atom economy is very similar to percentage yield. However, it differs by saying it is the sum of the molar masses of the desired product over the sum of the molar masses of all products times by 100. Now, these two are very similar but also very different, and I will have a video that explains the differences with some questions inside. Now, that is all the content done for chapter 3. Now, you don't know how much knowledge you actually have for this chapter until you do exam questions on it. I will have a video that covers exam style questions for this chapter very specifically, and I recommend you watch that video to make sure that you understand truly how this chapter goes. Thank you for watching, and I hope you have fun revising.